Dear students, today we will be learning about electromagnetic induction. So, our topic today is electromagnetic induction. Now, we all know that if we pass a current through a wire, this wire has magnetic field all around it. So, if you have a wire which is carrying a current, it has magnetic field all around it. That means electric current I can produce magnetic field. But the converse effect, that is production of electric current with the help of magnetism, is called electromagnetic induction. Now, before we start with electromagnetic induction, we must know some preliminary things. First of all, we must know what is known as flux, magnetic flux. Just as we have learned electric flux, we must know what is magnetic flux. Now, magnetic flux is nothing but the number of lines of force passing through an area. Now, if we have a magnet, say this is a magnet having a north pole and a south pole, we all know that the lines of force starts from the north pole and enters the south pole. The lines of force starts from the north pole and enters the south pole, like this. It starts from the north pole, and enters the south pole. Now, if we held a magnet in front of an area, this is an area, so if we held a magnet in front of an area, the magnetic lines of force will pass through this area. So the number of magnetic lines of force passing through this given area is called magnetic flux. So we know that this area is a special area and we know it as by area vector. So this area vector is A bar, and these are the number of lines of force that is passing through this area, and it is denoted by B bar. In electric field, it is represented by E bar. For magnetic field, it is represented by B bar. Now let an angle theta be between A bar and B bar. So this is the number of lines of force passing through this area. This area is a special area, it is a vector quantity. It is denoted by A bar, and the magnetic lines of force is denoted by B bar. The flux is denoted by phi. Flux phi is the number of lines of force passing through this area. The flux phi is defined as B bar dot A bar. It is a scalar product because phi is a number and so it is a scalar quantity. So the dot product of two vector quantity is a scalar quantity. Now we can open it. The dot product formula is mod B bar and mod A bar and then cos theta. This theta is the angle between A bar and B bar. Now if theta is equal to 90 degree, then flux phi is equal to 0. Now what does it mean? Theta 90 degree, flux phi is equal to 0. In other words, suppose this is an area and these are the magnetic lines of force that is entering this area. So suppose this is the area vector held by this pen, and these are the lines of forces. Now if this is the direction of lines of forces, if we turn the area vector by 90 degree, now this angle between magnetic lines of force and the area vector is 90 degree. no flux or no lines of force passes through this area, and hence we find that when theta is equal to 90 degree, flux phi equals to 0. If theta is equal to 0 degree, then flux phi is equal to B into A, mod B mod A. In other words, this is maximum, and when theta is equal to 90 degree, this is minimum. Now let's understand this. Theta 0 degree means this is the area vector and these are the magnetic lines of force. So when area vector and magnetic lines of force are in one direction, in the same direction, then the angle between them is 0 degree. Now this is a bit confusing here because magnetic lines of force is perpendicular to the area. But since this is an area vector, it has a special direction this way. And so magnetic lines of force and this area vector has or are in the same direction. That is why theta equal to 0. So theta 0 means this area is perpendicular to the direction of lines of forces. So theta 0 flux maximum, theta 90 degree flux minimum. It is just like this. Suppose you have lots of wind coming towards you. Now if you stand towards the wind will come and hit you. The maximum number of air molecules will come and hit you this way. So your area vector is this way and the direction of wind is also this way. So the angle between them is 0 degree. Flux is maximum. Now if the wind is going in this direction and if you turn this way, so your area vector is in this direction and the direction of wind is this direction. So the number of air particles hitting you in this direction is very less or minimum. So remember, theta 90 degree flux phi is 0. Theta 0 degree flux phi is maximum. So this is what is known as the electric or magnetic flux. Now let us come to the unit of phi. Now in SI unit, if B is 1 Tesla and area is 1 meter square, then flux phi is called 1 Weber. So 1 Weber is equal to Tesla meter square. That's the SI unit of flux. In CTS unit, we call it, here instead of magnetic flux in Tesla, we call it 1 Gauss, Gauss, into 1 centimeter square. So 1 Gauss into 1 centimeter square is 1 Maxwell. So CTS SI unit is Weber and CGS unit is Maxwell. Now here 1 Weber is equal to 1 Tesla into 1 meter square. So we can write it as 1 Tesla is 10 to the power of 4 Gauss into 100 centimeter whole square. So this comes to around 10 to the power of 8 Gauss centimeter square or 10 to the power of 8 Maxwell. So 1 Weber is equal to 10 to the power of 8 Maxwell. So these are the basic things that we know for electromagnetic induction. Now let us first understand how electromagnetic induction takes place. The study of electromagnetic induction is basically done by Michael Faraday. So While learning electromagnetic induction, first thing that we should know is the Faraday's experiment. Faraday, the great scientist, did a very simple experiment. He took a coil or a solenoid having lots of turns, and this was connected to a sensitive instrument called the galvanometer. Now remember I told you about galvanometer? Galvanometer is a sensitive instrument which can detect very small amount of current. So his module is having a coil and having a galvanometer, that's all, connected by wire. Now what he did is, he took a magnet having north pole and south pole. Now this magnet was rushed towards the coil. When the magnet rushed towards the coil, the galvanometer showed deflection. When the magnet rushed towards the coil, what happened? The lines of force from the magnet, now this is north pole, the lines of force comes up from the north pole and enters south pole. So here what happens? The lines of force was increased towards the coil. It was like this was the coil and this was the magnet, having said this is the north pole. And so the coil was pushed towards the magnet was pushed towards the coil. When the magnet was pushed towards the coil, the galvanometer showed deflection. Now, when the magnet was moved away from the coil, the galvanometer again showed deflection, but now in the opposite direction. Let me repeat. When the magnet was pushed towards the coil, the galvanometer showed deflection, say, towards the right. When the magnet was moving away from the coil, the deflection is towards the now left. In other words, the current in the coil is moving once in the clockwise direction and then the other times in the anti-clockwise direction, showing that when the magnet is moving towards or away from the coil, current is induced in it. In other words, production of electric current with the help of the magnet is known as electromagnetic induction. Now one very interesting thing he noted, that when the magnet is held stationary, in front of the coil, no current was induced. So it was like this, say this is the coil and this is the magnet. When you push the magnet towards the coil, the current is generated, or EMF is generated. When the magnet is moving away from the coil, the EMF is again generated but in the opposite direction. But when the magnet is held stationary, maybe very in front of the mouth of the coil, but it is stationary, not moving forward, backward, stationary, no current was induced. This led to three laws of Faraday. The first law is that the current is induced only when there is change in magnetic flux. This was the Faraday's first law. The current is induced only when there is a change in flux. Change in flux, in other words, the magnet is moving toward the coil or the magnet is moving away from the coil. Then only EMF is generated. Number two, the current is induced so long as the flux linked with it continues to change. So the current is generated as long as you move it. You move it forward or backward, only in that particular time the current is generated. And the third law of Faraday was that the induced EMF is directly proportional to rate of change of magnetic flux. Rate of change of magnetic flux. So this is phi b say. So phi b is the flux. So induced EMF is E proportional to d phi by dt. The faster you move towards the magnet, faster you move the magnet towards the coil, more is the EMF generated. If you move it slow, there is less flux change and less EMF is generated. So more EMF more the change in flux with respect to time, more is the EMF induced in the coil. So you can write it as E equals to some constant K into d phi V by dt. This is a constant. This constant depends upon the number of turns in coil, the number of the material with which the coil is made up of, and so on and so forth. Now here E equals to how much? You can write it as K into d phi V by dt. This minus sign is actually given by a scientist known as the Lenz. So we know it as the Lenz's law. The Lenz's law says that this coil, in this coil, the current is induced when you move the magnet towards it. When you move the magnet towards it, what happens is, in the face of the coil, suppose this is the north pole of the magnet, and you move the magnet towards the coil. You move towards the magnet towards the coil, and north pole is created in the coil itself. In other words, the current is moving in the anti-clockwise direction. Look how I have written north pole. The arrow in the end showing that it is moving in this direction. So what happens is, when you move the north pole towards it, and north pole is created. When you move the magnet with the north pole away from it, a south pole is created. Once again, this is the face of the coil here. This is the face of the coil here. What happens? Here what happens? This is the face of the coil. We take a magnet, and when we rush it towards the mouth of the coil, a north pole is created. Remember, this was a north pole, so a north pole will be created. If this was south pole, then south pole would have been created here. So this is the north pole. So you move the north pole towards the magnet, a north pole will be created. You move it away, a south pole will be created. In other words, for the north pole, the current is moving in the anti-clockwise direction, and when you move it backwards, it is moving in the clockwise direction. Now, when you move this magnet towards the coil, this is north pole, this is also north pole. North pole and north pole, there is a force of repulsion. North pole and north pole, force of repulsion. So when you move towards the coil, there is a force of repulsion. So when there is a force of repulsion, you have to push the magnet towards the coil. When you push the magnet towards the coil, you must do mechanical work. That mechanical work is converted into electrical energy, and the galvanometer shows deflection. When you take the north pole away from the face of the coil, a south pole is created here. And this north and south, there is a force of attraction. So when there is attraction, you have to pull the magnet away from the coil. When you pull the magnet away from the coil, you must do a mechanical work. That mechanical work is converted into electrical energy shown by the galvanometer. Remember, if we take the reverse, if we take a south pole will be created here. And when we move away, a north pole will be created here. So, what Lenz found is very interesting. That when we move the magnet towards the coil, there is a force of repulsion. And when we try to move the magnet away from the coil, there is again a force of attraction. So in both cases, we have to do mechanical work. And that mechanical work is converted to electrical energy. Now, what Lenz said is very interesting, that when we bring the magnet towards the coil, this coil repels the magnet. And when we try to move the magnet away from the coil, again this coil attracts the magnet. In other words, this coil does not want this magnet to move. So, a minus sign is being included here. The minus sign shows that the magnet is neither allowed to move towards the coil or doesn't allow to recede away from the coil. So that is called the Lenz's law. So for Lenz's law, we put a minus sign here. So this is known as the Faraday's law. This is known as the Faraday's law, and the minus sign is given by Lenz's law. So the Lenz's law says that this is the magnet which is causing current to move in the coil, and this magnet, this coil itself repels the magnet and attracts the magnet. This coil doesn't want this magnet to move towards or away from the coil. Because when we move towards the coil, we have to do mechanical work. When we have to move away from the coil, again we have to do mechanical work. So this current is generated only when we do mechanical work. So this is known as electromagnetic induction. This is the first law, known as the Faraday's law, followed by the Lenz's law, which gives you this degree sign. In the subsequent classes, we will be teaching more about electromagnetic induction. Thank you.